So my name is Liz Woodham, and I'm with...
I'm Charlie.
As we say, we're here in Cambridge and we're members of the Enrich team. We are very grateful to Trinity College here in Cambridge who fund these webinars so that they are free to you as participants. Perhaps you've been to one of our webinars before, and you're very welcome. Maybe this is your first time, and of course you're also very welcome. Before we get going on mathematics this afternoon, we're just going to give you a little bit of background and then get going properly. So I think we will share the screen, take you into the web browser. So I'm hoping that you can now see the secondary teachers landing page on Enrich. You can access this from the teacher menu on the left-hand side if you come to a different page. We've worked quite hard recently at Enrich, as many of you will know, to structure the website to reflect our beliefs and our ethos here. And so we'll talk you through that quickly, which will help frame what we're going to do this afternoon. So the tasks that we use are all linked to the curriculum, and if you as a teacher are particularly wanting to focus on that conceptual understanding or the fluency that mathematicians need, then the way to access the tasks would be to click here on our curriculum linked problems, and that takes you to the secondary mapping document. Let me click on here to show you quickly. Secondary mapping document at the top. And if I scroll down that page, you'll be able to see you can access the tasks via their curriculum area. So that's one way of getting to tasks on the Enrich site. Let's go back to the secondary teacher homepage. Alternatively, what you might want to do is have a focus on nurturing students' mathematical mindsets. So that is the third box here. So you're accessing the same tasks, so they're still curriculum linked tasks, but maybe you're interested in, just encouraging students to become more curious about the mathematics, helping them to work collaboratively and be more resourceful and resilient when it comes to solving mathematical problems. The third area, the third way in which we have, if you like, cut through the Enrich materials are by developing mathematical thinking skill. So if I click here to give you a sense, what we've done is we've thought about the process that you might go through if you're tackling a problem that you've never seen before. So Charlie, I think if we're given a new problem, the first thing we might do is try to make sense of it. We do a bit of that messy work, we do some exploration. Through that exploration, we might start to notice some patterns and start to get a bit of an insight into the problem. And from there, we often choose to work a bit more systematically because that makes the structure, it brings out the structure a bit. Having got a bit of a glimpse of the structure, we might then begin to sort of try to generalize the situation and make some conjectures. Now that, of course, is what we're going to focus on today, but just to give you a sense of this whole process, from the point of conjecturing, then we would lead on to trying to represent our mathematics, doing some visualizing maybe, and then to the final stage. Mathematicians are not happy just by getting a load of examples. They want to prove that what they think is true or is indeed not true. So that gives you a sense of those we're calling sort of 5 phases, if you like, of approaching a problem. And as I say, today we're part way through that process. We've already had a webinar about exploring and noticing and working systematically, which if you weren't able to participate in, you may like to watch the recordings of, and we'll show you where to find those shortly. But today we're focusing on conjecturing and generalizing, and we are going to be quite strict. So we're going to offer you a couple of problems from the site, but we really are not going to give you a chance to work on the nitty-gritty of the mathematics, and we're going to try and haul you back from going on to do any representing and any proof. And I think those things apply to us too. We will have to stop ourselves. Charlie, have I missed anything out there? Please add and and then we can go on to do some maths.
Yeah, no, I don't think so. I think, like Liz said, the problems, the rich tasks that we highlight that are in our mapping document, which address content, can be viewed from the perspective of the thinking skills that are required. So they are tagged with the appropriate thinking skills.
That's right.
But they're also can also be viewed from the mathematical mindset,
Yes.
because some of them might tap into students' curiosity, or some might be particularly good for working collaboratively.
Yeah.
And so we're sort of shining a torch on the problems, and they can be they can be tackled because you've got a curriculum objective in mind, or because you've got a thinking skill in mind, or because you've got sort of an attitudinal mindset objective in mind.
Yes.
And what I think makes enriched tasks rich tasks are that they tackle both curriculum and thinking skills, and require a sort of growth mindset, a mathematical mindset. So we're hoping to work on two problems. If there's time, maybe a third problem, to give you a flavour of what we have in mind.
Yeah. Okay, are we ready to do some mathematics then?
I think so.
Shall I share the visualizer instead of the web browser then?
Somebody.
Thank you. Right. Okay. So Charlie, I believe you've got we're going to set up the scene for us.
Right. So I might treat you as one of the students who might be in the class, as a representative, and I want us to imagine that I'm working with a class of I don't know, 11, 12, 13-year-olds.
Yeah, okay.
They've done some work on angles. And what you know about angles from previous lessons is that the angles in a triangle are up to 180 degrees.
Yep.
You know that isosceles triangles have got two equal sides and two equal angles.
Yep.
And you also know that about angles of quadrilaterals adding up to 360 degrees. And I think this is all you need to know.
Okay.
And we're going to assume that you've already had a lesson.
Okay, yeah.
And I'm not going to tell you what the title of this problem is, because it's sort of going to give away what the problem is. But what I did for a class of students is gave out a sheet, or showed a sheet, which had circles like this with 9 dots equally spaced around the circle.
Yeah.
And one of the questions that students were asked was, can they tell me what the angle is between each? I'll treat you as the student.
Please do.
What do you think the student said? What might you say?
Okay, well, if I've got 9 equally spaced dots, Charlie, I guess each of these angles at the centre, there are going to be 9 of them. They're all equal. I know we've got 360 altogether. 360 divided by 9, yeah, I think might be 40.
Okay, so we've got 40 degrees there.
Yeah.
And then the next question was that I gave sheets, I would have given sheets like this to all the students in the class, and asked them to draw all the possible triangles that they could, which had one vertex at the center.
Okay, yeah.
And here's the complete set that students would have come up with.
Yeah.
So after a bit of negotiating and convincing themselves that this is, and based on this information about the 40 degrees, we know that this will be 40 degrees.
Yeah.
This will be 2 lots of 40 degrees.
Yes.
This one here will be 40 plus 40 plus 40, 3 lots of 40 degrees.
Yes.
And this one, 1, 2, 3, 4 lots of 40 degrees, 160 degrees. And because all the triangles are isosceles, students were able to work out the other two angles
in each of these triangles. So that's relatively straightforward, isn't it?
So
good.
This nice practice at working out angles in triangles. And then the challenge was with a new sheet to draw some quadrilaterals where all four vertices were along the edge of the circle. So not using the center anymore. Okay. And here are some examples of the kinds of quadrilaterals that students might have drawn. So all four vertices along the circle, and here are a couple more. Okay. And then the challenge was, could they use this information to work out the angles of these quadrilaterals? And I'd like you to rehearse, Liz, what you think students might have done in this situation.
Okay, so I guess using what we've already done, we could annotate this, and could we draw in some lines to the center, Charlie, please? Yeah, great. Those are visible. Yeah, wonderful. So then we've created some triangles just like we had before. So hopefully this shouldn't be too taxing. Yes. So here I think at the center we've got an angle of 40 degrees.
So these would have been 70.
Absolutely. Yep. And so here we've got two lots of 40. So here we've got 80.
So these would have been 50s.
Yes. And then I think we've got three lots of 40. So we've got 120 in the middle there.
I'm going to write the 120 and the 80 and the 40 because at the end we might just check.
But it adds to 360.
360. And that way we can check that we haven't made any mistakes.
Very good thinking.
It's late in the afternoon.
Yeah.
So these are 30s, aren't they?
That's right.
Okay.
60 left. And then I think here we've got exactly the same, haven't we? We've got another 120 at the centre, and then 30.
That does out to 360.
Good, good.
Okay.
Okay. So I guess so your question was, can we find the angles of the quadrilateral?
Yeah.
So I guess all we need to do now is add these
okay. So 70 and 30.
We've got 100 there.
50 and 70.
120. I like the way you're pausing for me to do this.
50 and 30.
I think that makes 80. And then we've got a 60.
I've kept the easiest one to the end.
Thank you. Brilliant.
And so students all did something similar with their quadrilaterals.
Yeah.
Initially, I might have suggested that all their quadrilaterals included the center of the circle inside of the quadrilateral.
Because that way we can find the angles in exactly this way.
Yeah, it's much easier.
Yeah.
If students were to draw quadrilaterals which do not include, they can still use this information, but it's slightly trickier.
Just another step. Yeah. Yeah.
And we might do that. Okay.
Okay, so we can assume that as a class, we've generated quite a few examples of these quadrilaterals, and we've been able to find all the angles in them. Yeah, okay.
And then the next stage of the lesson would be to collate all that information.
Okay, yeah.
And so I might have asked the students to label the vertices of their quadrilaterals.
Yes.
And I don't mind where they start.
No.
Let's go back to this. So if they start with vertex A there, I don't mind whether they go clockwise or anti-clockwise. Okay. But once they start going in one direction, they've got to keep going. Okay. So that could be A, and that could be B, and that could be C, and that could be D.
Yes.
Sorry. If that was A and that was B, then that would have
to be C. Yes.
But likewise, if this is A,
you could have gone around.
We could have gone that way. And here we could start with A here and go in any direction that we wanted, as long as we carry on going in the same direction.
Okay.
And what was interesting, when we collated all the results, we got something like that on the board for students to be able to have a look.
So this is after quite a lot of work, isn't it? So we're massively speeding up the process for your benefit.
Because this,
is where
like you said, this was like what we did in the previous webinars,
Yes.
where we're doing exploring and noticing.
Yeah.
So, okay. So, is that in focus? Or...
It's okay. Yeah. Yeah, that's okay.
Okay.
Yeah.
Go for it. What do you
Right.
think students might have noticed?
So in our class, what we might have noticed, well, I have to say the thing that leaps out at me straight away is the fact that all of these measurements, all these numbers of degrees are multiples of 10. And actually, then looking a bit more closely, I think we would all notice that in fact they're all multiples of 20.
And the reason why I've chosen a 9-dot circle to start with is that the arithmetic is very easy.
Okay, nice. And we get these multiples.
We get multiples of 20. And it also means that if I'm wandering around the classroom and I'm looking over students' shoulders, I can tell straight away if they've made a mistake.
Yeah. When
they're, I mean, they might have made a mistake anyway and got angles which are multiples of 20, but chances are that they don't. I don't want the arithmetic to get in the way.
No.
Okay.
Great. Okay. What else might I notice? Well, I guess I might notice that in each of the quadrilaterals, so if I kind of look at a row which represents one quadrilateral, I can see that the angles sum to 360, and that links to one of the facts that I've now got in my toolbox anyway. But that's nice that all my quadrilaterals are sort of verifying that.
Yes.
And then perhaps if I look a bit more carefully at each row, I can see that for a particular quadrilateral, the sort of pairs of angles that are not adjacent to each other sum to 180 in each case. So we've got 120 and 60 here, 180, and here we've got 140 and 40, and here we've got 180. And this in these examples always seems to be the case.
So angles A and angle C, you're saying are up to 180?
I am saying that, yes.
And if they do, then we don't even need to check for B and D, because if we know that they're all at 360, then B and D have to add up to 180.
Good point. Yeah.
So, okay, so that's interesting and perhaps slightly unexpected. If we look back at our quadrilaterals, A and C add up to 180. What can you say about A and C in the quadrilateral?
Oh, I see what you mean. So these are sort of opposite, if you like. So it seems to be that the opposite angles of the quadrilateral are adding up to 180. So
A, B, C, D. A and C are opposite each other, B and D are opposite each other.
Exactly.
Okay.
Yes, I think going back to the image makes that much clearer, doesn't it? Okay.
Okay.
Yeah.
Now, we could just stop there.
Yeah,
and
say we've done a lot of very valuable mathematics.
Yes.
Yeah.
But part of this journey that you were talking about, which starts with exploration, working systematically, noticing, is that having done that, it's possibly given us a window into an area of mathematics.
Yes.
And there's an opportunity of moving from the particular to the general.
Right.
And this is something we'll talk about again and again when we are talking about conjecturing. So the initial examples give us a glimpse of what may be sort of behind a door, or we're looking through a window and we're giving a small view of what is there. But as mathematicians, it may be an opportunity to think more broadly, to more generally.
Yes.
And so the reason why we've got this phase in our problem-solving cycle, in our thinking skill, is that we can then encourage students to be thinking more generally.
Yeah.
So having seen these results, what might be the conjectures that you would want to make more generally?
Okay. So I might conjecture that, that, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118, 119, 120, Well, I'm thinking my conjecture would be that opposite angles of a quadrilateral drawn on a dotty grid, drawn on my 9-point dotty grid, add to 180 degrees. But go on.
Yeah. So that's very particular
It's
to a
very
9
particular.
dot. Would
So
you have a more general?
My general conjecture would be, well, I think that if I draw any quadrilateral, the opposite angles will add to 180 degrees.
Okay, and that seems a perfectly reasonable conjecture
from what we've got here.
For what we got. And as a well-prepared teacher as I am, I might have some 10-dot circles, some 12-dot circles, some 15-dot circles, and some 18-dot circles available.
Okay.
And what I might do is say to students, okay, Liz has got this conjecture that this is always going to happen, but we've only got very little evidence so far.
Yep.
So I might distribute some 10-dot circles to 1 or 2 tables, some 10, 12 dots to other tables, 15, 18. So different people in a different class can be testing out Liz's conjecture or Adam's conjecture, whoever it is. And that feels like a really nice mathematical thing to be doing. We're broadening our perspective, and we're going to fast forward. I'd like you to all imagine that this happened. And all the results get put up on the board, much like these results were put up. And we discover that yes, the opposite angles always have added to 180 degrees.
Okay.
And I might then ask you or the class, okay, so what do you think mathematicians ask themselves next? Or what is, does this confirm that your conjecture was valid?
And I think I might say, well, a mathematician, Charlie, I think has a sort of a healthy skepticism about any conjecture that they've created. So I might say, well, it does look like that at the moment, but hang on a moment. The circles we were trying were very much under your control. You gave us 10 dots, 12 dots, 15 dots, 18 dots, and we tried the 9 dot. These are suspiciously, I notice, all factors of 360. And I think I would like to test using dotty circles with a number of dots that isn't a factor. I don't know, like 7 or 11, for example, because I think, we have gathered lots of examples, but I feel as if we need to test some particular kinds of examples more. Okay. That's, I think, what I would say.
And I don't want you to be apologetic about being slightly skeptical,
no.
Because I think it's really important that we sort of test any conjecture sort of to the limit. And I know that John Mason talks about being skeptical, even being skeptical about the conjectures that we have ourselves.
Yeah.
Because initially we've got limited evidence to base our conjectures on. And so we want to, if we're going to be convinced of something, then we must try hard to disprove it.
That's right.
And I'd be delighted if students were skeptical and weren't convinced by my 9, 10, 12, 15, 18, and were asking themselves, wait a minute, why haven't we been offered 7, 11, 13, and so on? The lovely thing about this problem is there is a lovely proof to demonstrate that the opposite angles do always add up to 180 degrees. A proof that doesn't require algebra, a proof that just requires students to know the angle information that we've used. And we will return to this problem in one of our 2 future webinars when we're going to be talking about visualizing, representing, and about proof. And we're not going to give the end away today. Just like Liz said, we're just going to focus on conjecturing. But I hope this has given you all a feel for how one might work with a class and use an initial particular example to start broadening the perspective
That's right.
in the hope to be able to come up with generalizations,
That's right.
but later on might require proof.
That's
what's particularly nice about this is students are practicing what they know, what they need to know about in terms of being fluent, working out missing angles and triangles and the like. But they're also learning something new about cyclic quadrilaterals.
Yes.
So the problem is called cyclic quadrilaterals on the website.
We can reveal that now.
Yes. But of course, with 12-year-olds, that wouldn't mean anything.
No.
So,
no.
So they could learn one of the circle theorems through their own mathematical thinking and activity, rather than us having to spell it all out for them.
Exactly.
And the conjecturing stage is an important part. And apologies that we've rushed through the exploring and noticing, but if you want more about exploring and noticing, there are previous webinars where we focused on that, and we'll draw attention to them at the end of the session.
We will indeed. Brilliant. Thank you, Charlie. Shall we have a little go at one more example then?
Let's have a second example.
A second example for a task. And just while Charlie is getting a piece of paper ready, Robert, I know that you've asked a question about rich mathematical tasks. I feel that today's webinar is not the place to unpick that in detail, but we can, if you put rich task into the search on Enrich, you'll find an article. And I think one of the best places might be is to look at what we think and why we think it, and what we do and why we do it articles, and you will find more links.
There's also, if you go to the secondary teachers page, in the section at the bottom of that page, there is a link to enriching the secondary curriculum. And there you have links to the articles that Liz has been talking about, but there is also one about using rich tasks and what rich tasks are.
Thank you.
Oh, wait a minute! I've got my laptop open here, so I can.
Well, I could go here, but we could go quickly to it, and then we can go at the next task. So here we are back to. So if we went to the secondary teacher homepage. And we scroll down, Charlie, that's what you said,
yes,
wasn't it? Enrich in the second. So the link here gives you some articles, and that would be a good one to take a look at, Robert, that one there.
And we also have teaching secondary mathematics using enriched resources, and teaching using rich tasks, and enriched resources for every occasion. So all of that is to do with...
Good place to go.
Yes.
Thanks for your question. Okay, so Charlie, let's have a go at another task with a different focus this time. Let's share the visualizer once again. Okay.
Okay, so there is a problem on the site called Wipeout.
Yep. And
it starts by asking us to consider 6 consecutive numbers and imagine that we've spilled a bit of tea and one of the numbers has been wiped out. And might it be possible that the remaining 5 numbers have an average, which is a whole number?
Okay.
So that's the initial challenge.
Yeah.
And like Liz said, we're not going to give anybody any time to do the exploring and noticing and working systematically. And we're just going to assume that
that has been done in the class.
And Liz, what would students have found if they'd been working with these 6 consecutive numbers?
So here an example of 4 sets of 6 consecutive numbers. And in this here with the numbers 1 to 6, we found that we could wipe out the number 1 and we would get a whole number average from the remaining 5.
Okay.
But we also found actually that you could wipe out, instead, you could wipe out the number 6 and you could get a whole number average from the numbers 1 to 5.
Okay.
When it came to this set of consecutive numbers, we found that you could wipe out the 4 to get a whole number average, or instead you could wipe out the 9. And with the numbers 10 to 15, we could wipe out the 10. or we could wipe out the 15.
Okay.
And from 107 to 112, we could wipe out the 107, or we could wipe out the 112.
Okay. So here's yet another example where students have done some useful work on averages, but there's been sort of a bigger question, a slightly more interesting question perhaps, but more importantly, there's a chance to notice something.
Yeah.
So
okay. So I guess what the class we've noticed is that when we have a set of 6 consecutive numbers, we can always wipe out the lowest number, or we can wipe out the highest number, and the remaining 5 numbers will have a whole number average. That's what I think that's what we would notice.
And that would be a reasonable thing.
Based on all the examples that we've done.
And that might lead to 1 or 2 conjectures.
Yeah, okay. So I think a conjecture how we might have more generally would be that, well, I think that if I had any set of consecutive numbers, my conjecture is that I will be able to wipe out the lowest number, or I could wipe out the highest number. And by any set, I mean here we've got 6 consecutive numbers. I'm going to suggest that my conjecture is that I could do that with 5 numbers. I could do that with 6 numbers, I could do it with 7, I could do it with 8. That would be my conjecture. Okay,
and that seems to me a perfectly reasonable conjecture based on the evidence so far.
Okay.
And okay. So we might then give students time to work on some more examples, and this would be part of what they would do in the lesson. Yeah. And let's imagine that some students have tested Liz's conjecture with 4 consecutive numbers, with 5 consecutive numbers, didn't bother with 6 because we'd already done that, 7 consecutive numbers and 8 consecutive numbers. So what? Okay,
so we discovered, Charlie, that in this case, we could wipe out the 5, and we would have a whole number average, or alternatively, we could wipe out the 9 and have a whole number average. In this case, we discovered that we could wipe out the 12 and get a whole number average. Here,
and that was the only
way. Sorry, I should have said that. That was the only way we could do it.
Okay.
So yeah, in this case, here when we decided that we could wipe out only the 9 to get a whole number average. Okay, and then when it came to this example, we decided we could. Well, we didn't decide. We discovered that we could wipe out 4. And alternatively, we could wipe out the 11. So actually, we've refuted my conjecture.
Okay. So we talk about, we don't quite like talking about conjectures being right or wrong.
No.
But we like to, on the new evidence, we might have to modify our conjecture.
Right. Yeah, well, I like that idea of modifying the conjecture. As you say, new evidence has come to light. So I can tweak what my conjecture is.
So what the original conjecture was completely reasonable.
Yeah, based on what we've done.
But
yeah.
So we'd like to invite you. I'm sorry it's taken quite a long time before we get round to asking you to write anything in the chat. Could you suggest what your modified conjectures might be based on the evidence so far? So if you can use the chat, we'll keep quiet for a minute or 2. Okay, fantastic. It seems we won't spoil anybody's fun by giving away what people are writing, but it seems to me people are taking the evidence that they have so far and making perfectly reasonable conjectures. And I'd expect students to be able to make similar conjectures, having explored, worked systematically, because you can imagine initially working on 6 consecutive numbers in a fairly random way, but then the idea of saying, okay, let's take 4, then 5, then 6, then 7, then 8 consecutive numbers. And by working systematically, you're much more likely to notice a pattern and notice what's going on. And people have been commenting about either having an even number of numbers or an odd number of numbers and so on. Now, this is only halfway through the journey, because after this, one would want students to try and understand why some of these things are happening, and to understand, to have a feel for this, and then to be able to come up with convincing arguments of why their conjectures or why the generalizations occur are always true. So there's the visualizing, representing, but it is also coming up with justifications and convincing arguments and proofs.
That's right.
And this is what we'll do in the next couple of webinars. And we are very likely to come back to this problem because, again, there's a lovely way of looking at this, which doesn't involve any algebra, which is quite accessible to students. And again, the reason for choosing this problem is that we want students to do some work on averages. But it's nice to be working on averages and working on those mathematical skills which involve, in particular, generalizing and proving. So we're building up, not to just be able to answer the first question, but to be able to answer and understand a more general question.
That's what Colin Foster calls purposeful practice. It's his kind of, rather than just streams of isolated examples. Okay, thanks, Charlie. Brilliant. What we'd really like to do now is to share with you on the site where you can find more of the guidance that we've written and sets of resources which we hope will give you the opportunities to encourage your students to conjecture and generalize. So I'm going to go back to sharing the browser. So here we are, we're back on the this particular page, which we got to from the secondary teacher homepage. Now, if you have come to these webinars before, you will be familiar with the fact that we are creating a bank of resources on our Problem Solving Schools page. Perhaps you are here because your school has recently become a problem solving school. And if you have never heard of Problem Solving Schools before, then do take a look at this page. If I scroll down to this main page and click on the right box here, the resources and professional development, you can get a sense of what we've done before. So we're now on the sort of the fourth webinar in our Problem Solving Schools series, and the third in the particular series of developing mathematical thinking skills. So here you can revisit previous webinars if you wish to. And
there are, yes, so there's a guidance and the links to the webinar.
Sorry, guidance and links to the webinars. I should be more specific. So on this page here, we've developed some guidance, particularly about conjecturing and generalizing, which we'll give you a quick overview in a moment. But we just wanted to draw your attention to the fact that as well as some general guidance, we have exemplified what we mean using a few Enrich tasks, including Wipeout, which is the task that we've just had a go at together. So we've really, all we've got on the website here, it reflects the kind of conversations that Charlie and I have just had for you, with you participating in some modified conjectures. So I can just click here. So it's giving you a sample of what students might have found as they'd worked on 6 consecutive numbers. Here are some possible conjectures that students might have come up with. And then having tested out some of these are some possible modified conjectures. So the same sort of sequence that we did with you. But, and as I say, we've included quite a few different tasks there, which we've exemplified for you, and we've ordered them as far as we can in sort of order of mathematical experience, if you like. So Thank you, Charlie. The tasks at the top will be suitable for sort of middle upper primary, and then going down all the way to upper secondary. Did you want to show another one in particular, Charlie?
We haven't exemplified cyclic quadrilaterals.
Good point.
But there is tilted squares, which is very, very similar in structure.
Yes.
It leads to Pythagoras' theorem in the way the cyclic quadrilaterals led to the circle theorem about the opposite angles. And it's organized in much the same way as we've been talking about it. And I'm drawing attention to it because there is a video to it in the teacher's resources to tilted squares. So if you would like a sort of a less rushed view of what it might be like to work on a task like this,
in the classroom, that's right.
Then you could have a look. You could have a look at that.
Yeah.
And there were initial conjectures, follow-up conjectures that needed modifying, and so on. And that's nice. Yeah. And we did a similar webinar yesterday for primary teachers. Yeah. And we exemplified two of the problems. Two of the problems Magic V's and Got It.
And Got It, both of which we've written a bit there. And actually the recording of yesterday's webinar is here at the top of the page, which is where we will also add this recording. So of course, do share that with colleagues or watch yourself if you're interested in the primary age range.
But also Magic V's and Got It are also very suitable for year 7 students.
They are indeed.
We've both worked with
Absolutely.
Lower secondary and got a lot of mileage out of those two problems. So you may want to, which is why we haven't put ages,
yeah.
Because quite a lot of, well, a bit like the cyclic quadrilaterals, you didn't need very much angle knowledge.
Year 6 angle knowledge is sufficient.
It would be sufficient.
Yeah. So if I'm just, this is the top of the page again, so let's just give you a quick overview of the way that we've structured the sort of the main part of the guidance. What we're doing is we're offering you some things to think about if you are wanting to encourage your students to conjecture and generalize, and give them those opportunities. Charlie made the point earlier about this idea that we've chosen problems which offer a small, initially give you a sense of a little window into the general structure. In contrast to what often happens, I guess, is that students go from a question to a different question to a different question to a different question, and we're offering sort of question to general. So it's just a slightly different model, exemplifying this, this key process that we've been talking about. We've set this guidance up in a way that we've done in the past, similarly for exploring and noticing. We've started out with some setting out some of the, Enrich's values, which inform what we do and therefore impact in what happens in the classroom. I think one of the key points to draw out in this sense is that we firmly believe that everyone can conjecture, and creating a conjecturing atmosphere is about taking away the idea that you have to be sure in order to verbalize your thinking, and that actually we want students to be comfortable in expressing something that they're not yet certain about. But as we were saying earlier, a conjecture is based on the evidence we have at that time. And John Mason talks about treating everything that's said as a conjecture, doesn't he? Which is an interesting way of thinking about things.
And it seems a good idea to, yes, encourage everybody, not just those who are certain about things. I have been at one of John's sessions, and he explicitly asked the people who were uncertain to do the talking, and those who thought that they knew how to proceed to keep very quiet. And what was interesting is that when the people who were uncertain spoke, those who had thought that they were certain all of a sudden started realizing that perhaps there were one or two things that they hadn't thought through or they hadn't considered.
Right. Interesting, isn't it? Yeah. So this links very nicely to what we would call structural considerations. So kind of the considerations which you need to think about, the way that your maths lessons are framed, and the kind of way that you would, what am I trying to say? It could be about structuring the classroom, it could be physically structuring, but sort of facilitating conversations in the classroom. So for example, here we've talked about the use of common boards. So Charlie, we were imagining that we were gathering together students' results, but then what we also might do is we might write up students' conjectures, because of course in a classroom environment, each student might have, well, not necessarily each student, but there will be lots of different conjectures which may go up on a board. And then this idea of common boards means that everybody in the class had the opportunity to add to the board themselves. So it could be that you found an example which refutes a conjecture, so you could pop that up next to the conjecture. You may offer an example which, perhaps an extreme example, which still backs up the conjecture. But it means that it doesn't have to be orchestrated in a whole class way with everybody listening to one person. It can be done throughout a lesson at the student's own pace.
Yes, yeah. I mean, one of the third bullet point is something that I think we've heard Anne Watson talk about,
Yeah.
making the private public. I suspect when you and I were students in classes, all our work happened in an exercise book that only we could see and the teacher would see. It was very much private.
Absolutely.
Kind of thing.
Absolutely.
And the Common Boards allows for us, for the students to work, well, to create a community of mathematicians in our classroom.
Yeah.
Would be one way of talking about this.
Yeah.
And to recognize that we're going on a journey, but also it means that we're not all having to test the 10 dot, the 12 dot, the 15 dot, the 18 dot. We can share that out and bring results together so that we can then dedicate a bit more time to noticing patterns, to conjecturing, and later to generalizing, based on a lot more information than we would be able to gather if we were working all separately.
Absolutely, yeah. And the final section of our guidance here relates to sort of the nitty-gritty interactions in the classroom. So we've offered some prompts that you might use, some questions and prompts that you might use for students to encourage them to begin to conjecture and generalize. We've made this, but we like this phrase, scaffolding and fading. So the prompts at first, if they're not used to these kind of ways of working, students may require you to prompt them more frequently. But the idea is that gradually this scaffolding fades, and in time, students may ask these questions of themselves, or you may think about, as a nice phrase, what would a mathematician ask? Or indeed, you may say to students, what am I going to ask you next? As a little cues for students to begin to do this thinking for themselves. So we hope you find that guidance useful. And as we say, we've put those examples at the bottom, but there are also, if we go back to the Problem Solving Schools page, we've also gathered together collections of tasks which lend themselves to giving students opportunities to conjecture and generalize, and they're all organised by year group. So we hope that even if the tasks we today have had a look at aren't suitable for the particular students you work with, you will find something in those collections to work on with them.
Yes, indeed.
So I think that brings us to the end of this webinar, almost.
One thing I think I'd like to mention is, well, we're assuming most of you, or all of you, receive our newsletter, which will go out later this week. There'll be a link to these resources, but also reminding you that we've got some live problems.
Yes. And
the current live problems, which were published today, are to do with conjecturing and generalizing. And one of them there are two secondary ones, and one of them is Wipeout. Yeah. So if you're doing some work on averages, or would like your students to do some work on averages, then Wipeout might be an interesting problem. We've got two problems which seem identical. One's called Got It, and one is called Have You Got It? One is used at primary and one's used at secondary, so I think that's why they've got different names. Yes. But Have You Got It is our other live problem at secondary. You could watch yesterday's webinar and catch the bit that we did where we discussed Got It to give you a flavour of how you can use this for encouraging students to conjecture and generalise too.
Absolutely. And I think the final thing we'd like to share with you before we say goodbye is that we have just published some summer challenges. The link is in the top box up here. What we've done is we've gathered together some resources that we feel particularly lend themselves to being worked on at home. So if you'd like your students to continue thinking mathematically over the summer, you may wish to share these resources with families. Or alternatively, what you could do is to select a few particular resources from these collections, and you could let students know that perhaps you're going to return to them at the beginning of next term. That's an alternative way of doing it. But we hope there is something there for everybody should they wish to.
Yes, we're used to the music department telling parents about concerts, and the drama department telling to parents all about theatre productions, and the athletic PE department telling parents about the successes of netball and rugby and football and cricket and athletics team. It'd be quite nice to have messages included in newsletters to parents about what the maths department is offering.
Absolutely.
And so in the past we've offered summer challenges but published them much later in the term, and it hasn't been possible to share that with parents. We're hoping some of you may want to share this with your parents and encourage your students to have a go on those rainy days in South Wales and the Pembrokeshire coast or something.
Yeah, the only reason Charlie said that is because that's where I will be going on holiday. Yeah. Thank you all very much for your time and for participating on the chat. We hope that you found this useful. Please do give us your feedback. I've just popped the link to the feedback form in the chat. We do hope to see you again at a future webinar. Our next one is in October. You can find the dates on our events page. And in the meantime, have a good rest of your evening.
And the rest of the term.
And the rest of the term. Yeah.
And a nice summer holiday when it comes.
And that is. Thank you very much indeed, all of you, and goodbye.